Hi class, welcome back to thermodynamics. In this lecture, we are going to be looking at the definition of the Clausius inequality. Now, this unit we have been focusing on the second law of thermodynamics, which says that in an isolated system, entropy can never decrease, it can only increase. In other words, entropy can be created but never destroyed. Now, Rudolf Clausius sought to explain the relationship between heat flow between a system and its surroundings and also the entropy of a system. And he is the one that gave entropy its name, and he sought to define entropy quantitatively. And now with his theorem that we're going to be looking at today, he is doing just that. This theorem is used to determine whether a process is reversible or irreversible. So hopefully you watched that crash course video for a little review of what a reversible process is versus an irreversible process. And of course, in nature, we can get close to reversible, but no process is perfectly reversible. So all natural processes are irreversible, and as engineers, we seek to get them as close to reversible as we can to improve their efficiency. Also, looking at the second law of thermodynamics, we've looked at two definitions, two statements of the second law so far. We looked at the Kelvin-Planck statement, which said that it is not possible to draw energy just from one thermal reservoir to produce work done by the system. Equivalently, and hopefully you watched this video as well, posted as a refresher, looking at the equality between the Kelvin-Planck statement and the Clausius statement of the second law. And the Clausius statement of the second law says that it is not possible for heat to flow from a lower temperature to a higher temperature without putting work into the system. Okay, so with that summary, let's get started now and look at the Clausius inequality. So, looking at the Clausius inequality, let's just write this out. So, it is going to be the cyclical integral. Okay, so this is the sum over a cycle. That's what that circle right there is. Of this infinitesimal, that's what this curly d is, this del, is some infinitesimal exchange in heat Q with a system and its external reservoir, divided by the temperature of the surroundings, and this is going to happen across a boundary. That's what that B is, right? And remember, we talked about the definition of a system, and a system is defined by its boundary, right? The boundary distinguishes a system from its surroundings. Okay, so Clausius wrote that, so if you sum up the heat exchange between surroundings, the external reservoir, and a system throughout an entire cycle, and divide it by the temperature of the surroundings, then this is going to be less than or equal to let's just actually start with equality. This is going to be equal to minus sigma cycle. Okay, and what this minus sigma cycle gets at is it's Clausius quantifying how close a system, a cycle, is to being reversible. So how close is it? So the closer we get to zero, the closer to reversible it is. So if we are equal to zero, if minus sigma cycle is equal to zero, then we say the cycle is reversible. It would be a reversible process. If it were less than zero, then what we have is an irreversible process. And if we were greater than zero, that is not possible. So that cycle would not be possible. And looking at this, if you take into account the double negative here for being negative and less than zero, this would just mean sigma cycle. And here would be minus sigma cycle. Okay. So in other words, another way to look at this would be for two reservoirs. QH over TH, so the heat transfer from the higher temperature thermal reservoir minus heat transfer to the cooler thermal reservoir is going to be less than or equal to zero. So this is yet again another piece of the puzzle that we can use for trying to determine whether a process is possible, to figure out maybe what the temperature of the cool reservoir or the hotter reservoir must be, or or to quantify heat exchange. Okay. And of course, the higher the temperature, the greater the heat transfer, so the greater the difference in temperatures, the more entropy. So let's go through and go through an exercise together. So this is number 89 from chapter 5 in your book, and it says, at steady state, a thermodynamic cycle operating between hot and cold reservoirs at 1000 Kelvin and 500 Kelvin, respectively, receives energy by heat transfer from the hot reservoir at a rate of 1500 kilowatts. It discharges energy by heat transfer to the cold reservoir and develops power at a rate of, there are three different cases that we're going to look at. A, 1000 kilowatts, B, 750 kilowatts, and C, 0 kilowatts. So for each case, we're going to go through and we are going to apply the Clausius inequality on a time rate basis. So with respect to time, so we'll be looking at Q dot, W dot. All right, so we're looking at power here, right? Energy per time is power, to determine whether the cycle operates reversibly, operates irreversibly, or is impossible. So let's start out with A. And let me just write our givens up above. So we have that, let's see, TH is 1000 Kelvin. we have that Tc is 500 Kelvin, and we have that QH is 1500 kilowatts. So now we are given that W cycle, W dot cycle, because it's a rate, is 1000 kilowatts. So by definition, W dot cycle is going to be Q dot H minus Q dot C. So the heat exchange from the higher temperature thermal reservoir to the system, and the heat transfer from the system to the cooler thermal reservoir. And so now we're given our Q dot H. Put that dot back in. We're given our Q dot H, and we're given our W dot cycle, so we can solve for Q dot C. So Q dot C is going to be equal to Q dot H minus W dot cycle. Okay, and so this is going to be equal to 1500 minus 1000 kilowatts. So it is going to be 500 kilowatts. All right, so now we need to go through and apply the Clausius inequality. And that says that sigma dot cycle is going to equal Q dot H, or Q dot C, sorry, Q dot C over Tc minus Q dot H over TH. Right, because minus sigma cycle is going to be Q dot H over TH minus Q dot C over TC. So let's just deal with this in the positive. So what we end up getting is going to be sigma dot cycle is going to be 500 kilowatts divided by Tc, which is 500 Kelvin, minus 1500 kilowatts over 1000 Kelvin, or TH. And this is going to give us a sigma dot cycle of minus 0.5 kilowatts per Kelvin. All right, so that gives us a negative sigma dot cycle. So if you look back at our definition, having a negative sigma cycle tells us that this process is not possible. Okay, so this is impossible. Okay, so let's look at the next one now, part B. And let me just summarize once again that we had TH is 1000 Kelvin, TC is 500 Kelvin, and QH, Q dot H, is going to be 1500 kilowatts. Okay, so part B. That was, we're given that W dot cycle is going to be 750 kilowatts. Okay, so this is the amount of energy produced by the system, and this is going to be equal to Q dot H once again minus Q dot C. And so Q dot C is going to be equal to Q dot H minus W dot cycle, which in this case is going to be 1500 minus 750, which is going to give us 750 kilowatts. And then we can calculate sigma dot cycle, which is once again going to be Q dot C over TC minus Q dot H over TH, which is going to be 750 kilowatts over 500 Kelvin minus 1500 kilowatts over 1000 Kelvin, which is going to give us 0 kilowatts per Kelvin. Okay, so that tells us that this cycle is reversible. Okay, let's do one more. So C, we're given that W dot cycle is going to be 0 kilowatts. So that'll tell us that Q dot C is going to be Q dot H, which is 1500 kilowatts, minus W dot cycle, which was 0. So this is going to be 1500 kilowatts. So sigma dot cycle is going to be equal to 1500 kilowatts divided by 500 Kelvin minus 1500 kilowatts divided by 1000 Kelvin, which is going to give us 1.5 kilowatts per Kelvin. All right, so looking back once again on our last sheet with our definition of the Clausius inequality, if we have a positive sigma cycle or sigma dot cycle when you're looking at QC over TC minus QH over TH, then we are going to have an irreversible cycle. So let's just be clear down here. This is our definition of minus sigma cycle. So minus sigma cycle is QH over TH minus QC over TC. And so sigma cycle is going to be QC over TC minus QH over TH. Let me just make C a little more clear down here. Okay, so going back to our problem, we get that this is going to be an irreversible cycle. I'm just going to abbreviate it. Okay, so that is all I have for you today, and I will see you next time or next lecture when we are going to explore entropy as a property. So we're going to break into our property tables once again for entropy. So I'll see you then.